Welcome to class number 6. I guess I didn't do class number 5. I don't know why. Must have run out of time. So we're entering chapter 3. This is section 3.1. And we're going to start with doing things with rigid bodies and equivalent systems of forces and moments. So here's the bottom line up front. Now, the real important thing is we're no longer dealing with particles. And so our free body diagrams are going to have shapes, right? So the idea in a rigid body is that now the location of the forces actually matters. When we treat something like a particle, or something that's very small, it's basically we can treat just about anything like a particle just as long as the forces, where the location of the forces on the body don't matter. But when it has some kind of shape and size to it and the actual physical location on the body matters, we have to consider what the moments are, right? So that's the idea with the rigid body. And so here's the fundamental equation that we include, right? We had the summation of forces equal to 0. Now we have the summation of moments, and we could even make this a vector, right? Just so you know. The most straightforward moment, right? So we're about to go into a bunch of vector stuff, but we want to keep sight of the real important thing, that a moment is just a force times a distance, but it's a particular distance. It isn't just any distance. It's a distance that is perpendicular, right? So it's the distance to the moment that we're taking the thing about, and we usually go subscript to define where we're taking a moment about. And if we draw the force, it has a line of action. And that line of action continues off into space. And so it's only the distance. We have to find a distance here. This D, we're just using that generically as a D, defines the distance that will create a moment, right? So it's no other distance except for the one that's perpendicular to the line of action. In a more complicated sense, in 3 dimensions, what we want to do is take a position vector that we'll define as the position. In this case, we should be saying, if this was correct right here, this should actually be O right here, if it was going to match this figure. And that's going to be point A is a point where the force, a line of action of the passes through of the force, and this position vector R right here, we could call it, if we want to make it very, very formalized, we could say that's A with respect to O, right? So that's, we're starting at O and we're finding A, and that's how we define the thing. So we have a distance, the X direction, Y direction, and Z direction, and then we have a force vector that's out here that we could break down into 3 components to be 3-dimensional. If we want to find the moment, we take the cross product of the position vector crossed to the force vector. And there's a number of different ways that we could write that out when we do a cross product. But I think the most consistent way to do it is to take the determinant of a 3x3 matrix, where we have on the top row the unit vectors. On the middle row, we have the position components of the position vectors, and then on the bottom we have the components of the force vectors. So that's the bottom line up front when we want to treat something. I will mention that this right here is an equivalent moment, okay? And when we come up here, we're always looking for the reaction moments, all right? So this chapter kind of takes like a little bit of a regression, once again, and where we're looking for the resultant of forces, remember in the beginning, and then we took a free body diagram to find the reactions, right? To figure out what the resultant would be equal to 0. But now, once again, we're taking a step backwards, and we're looking at and the resultant is an equivalent force. Now we're looking at an equivalent moment. I will try to emphasize the free body diagram because I don't want that to be diluted. right? So I'm going to take a slight deviation from some of the sample problems. So when you look at them, please focus in on this difference that I'm trying to make, because I don't want you, I'm trying to get so you won't be confused, and hopefully this will serve to not confuse you. So we're reiterating some things from the bottom line up front when it comes to forces and moments. I just want to emphasize the difference between external and internal forces. External forces are things that are applied, right? So when we make a free body diagram, we are cutting things off from the rest of the world, and the piece floats. So we shouldn't show the people in the free body diagram, and we shouldn't show the ground in the free body diagram. And we take a look at all the forces. So there's applied forces. That would be the people trying to pull this. We would have reaction forces. So those are really going to be things like the ground right here. And by the way, when it comes to this free body diagram, because we are dealing with statics, there actually has to be some amount of force in the opposite direction of this applied one. So we'd actually want to put in the friction force on there. Otherwise, it's going to move if there isn't a opposite direction force. And, so we would put like the brakes would be on this and they're trying to pull it because it's static. If it was dynamic, we have a different treatment, but that's next semester, right? And then also, we want to also include in the external forces, gravity. Don't forget gravity right here. That weight right there is pulling on the center down. But internal forces might be, the axle. So is axle E-L or L-E? I don't know. The axle on the wheel or on the tire, right? But those are inside the free body diagram, so they don't show up. Or we might even have like, maybe there's like some kind of connection here, internal. You could think of maybe the chassis is somehow bolted to the frame or whatever. So there's like internal connections between there. And if we wanted to find those forces, we would have to break it apart and make a separate free body diagram and have the thing floating. Well, this happens also with moments. Moments can also be internal, right? As this is just an example. So that goes EG, right? And not EI, but EG, that kind of thing. Just trying to emphasize, right? So the difference now that we're dealing with is that we're dealing with a rigid body that has geometry, and the location of the load of the object matters. But still, we have something that we want to take a look at. We have this property called transmissibility. So we're introducing something, we might have alluded to it. And this has like equivalent forces, one idea. That the idea of transmissibility is that it doesn't matter where this force is located along the line of action, just as long as it's along the same line of action. The force can be equivalent. We'll see later on when we move it to some other place other than along the line of action, there's a consequence that ends up being a moment. Sometimes we'll call it a couple. So some of these other examples right here, we could be pushing this, pulling this, or we could be pushing this. It doesn't matter in terms of the results that we would get when we were looking for maybe the distribution of these loads. Because these different loads, they could be different depending on the height of this force. Like if we push the height up there, yes, now it's going to be different. Like if we were pulling it up here, it could be different than if we're pulling it down there. But as long as these forces are along the same line, they're going to be equivalent forces. And then there's other examples here, right, where we could say we could just move this force over to right here, and we could see, okay, now if they equal to each other, they'll balance out, right? And the same thing here, we could move this force, move it to right there, equal and opposite, that's fine, right? So this one is equivalent to this one, is what we're saying in transmissibility. Not a big, heavy lift. here's where we start getting a little bit more mathy, right? So this is just a math review or an introduction, depending on whether you've ever seen this before. And I'm going to stop in class and I'm going to ask this. Have you covered cross products in other courses? What course, and do you remember what they mean, what a cross product is? Well, if not, that's fine. So the vector product, which I will emphasize is another name of the cross product, is represented by this big X. It's not a times exactly. It's like an over-exaggerated X. And we take one vector and we cross it against another, and the order of these operation matters. We'll review that, but you can't Q crossed with P does not equal P crossed with Q, right? That matters. And the concept of this is that if we have these two vectors, and regardless of what the two vectors are, there's always going to be a plane, a single plane, a unique plane that they lie upon. Like those two vectors define a plane. And the cross product is going to be something that's perpendicular to that plane. And it's going to be a new vector. You'll notice that these are all vectors, right? And we'll see that there's a, his twin or his buddy, the dot product, that is actually different. That ends up being a scalar. But in the cross product, it ends up remaining another vector. And that vector is going to be perpendicular to the plane, and we're going to follow something we call the right-hand rule, right? So we'll take a look and we'll curl the fingers around the direction. And here I'll even start, right? So we're crossing P onto Q. So we take our fingers and we roll them along that P towards the Q, and our thumb points upwards, and that determines the direction of the new vector. And if we want to get the magnitude of it, we take the magnitude of P, the magnitude of Q, and any angle that we might have behind it. But then generally speaking, it's only when we might have a situation where it's easily defined or we already know what that angle is before there that we would actually do, right? But the most important thing is the direction is perpendicular to the plane. And this is following the right-hand rule. So a lot of times I'll go R, H, R to make sure we remember that. It's also good to take a look at the differences between, okay, so we also can cross product the unit vectors, I and J. So what we do, and I have a little diagram of this here, but if we take I and we curl our fingers, right, with our hand, like, maybe I'll try to draw a little hand, and this is a right hand right here. There you go. Not very good. Right there. We're curling our hand. Here's our fingers, and they're curling around, and our thumb is pointing in this K direction, which is along the Z. If we go the other direction here, and once again, it has to be our right hand, and we curl our fingers in this direction, our thumb is going to point in the negative Z direction. So one idea is to, when you're setting this thing up, is to draw a little axis right here, right? And then for whatever thing that you're doing, use your right hand. And I'll show you all the different variations. Cross product properties to note, as I alluded to it, Q cross P does not equal P cross Q. It actually ends up being the negative, right? So that's like, if you take the right hand rule, you'll see, obviously, if you cross one into the other, as opposed to the other one, your thumb points in along the opposite direction. We also have the distributive property, right? So if you take P and you cross against Q plus Q inside these parentheses, then it's P cross Q1 plus P cross Q2. This does not hold true in the order of operations when there's a cross product inside of parentheses. So these are things that we want to pick up. All right, so here's the different combinations if you had two vectors, unit vectors that are crossed against each other. We need to know this because we will be able to, when we apply something in a second, be able to cross product all these things and distribute them out. And we'll see that quite often it's the unit vectors that get crossed with each other. So I crossed with I is 0, J crossed with J is 0, K crossed with K is 0. That just sort of like for one thing, you could use this as your rationale between there. Then theta right here is going to be either 0 or it could be 180 actually to each other, right? So it doesn't matter which one it is. Either way, the sign of 0 or 180 is equal to 0. So therefore, crossing against each other just kind of makes sense. Now these other ones, you could memorize them, or you could use the right-hand rule, or you can use this little thing that they have in the book here where they're trying to tell you that clockwise is negative and counterclockwise is positive, right? If you draw something, if you draw the I, J, K. I prefer this way right here, and this is actually my hand. I traced it out. I took a picture of my hand, and then I traced it out. This is excerpt from my book. But you can see how I crosses into J ends up with a positive K, right? And that shows up right here. J crossed with K right here is a positive I, right? It's pointing towards I. If you take a K and you cross it with I, K crossed with I right here is a positive J, right? It's pointing upwards. And then all the same things right here, right? So you accept the opposite direction here. J crossed with I. Instead, you'll notice that you're in the negative K direction. You get the idea. And if you memorize this idea here, then you can always figure the thing out. So practice it a little bit and work your way through it, and you'll see that you can always get the right thing. So here's an implementation of a generic thing where you'll see how this works out and why you would use it, right? So here's the distributed property being shown. Well, no, it hasn't been shown yet, all right? So here is what the vector, this generic vector P looks like, and the generic vector Q looks like with their coefficients in front of the unit vectors. I'm not going to do all of them out here, but let's just go through. We would start to do the distribution, right? We would go Px times Qx, right? And these are just scalar components. So that's the same thing as just multiplying by them and then take the I and cross it against the I, right? And I won't make the decision yet about what to do with them. Nonetheless, I'll take the PX and the QY, right? You're just systematically coming through this right here. And that's going to be I crossed with J, right there, right? I crossed with J. Now let's take the PX and times the QZ. That's the I crossed with K. All right, now let's take the PY and cross it. So PY QX. And that's going to be J crossed with I. And then take the PY, cross it with the QY. And that's going to be J crossed with J, and so on. You get the idea. But now you start to go back and look at what we had up above right here, or we just memorize the thing. Either we memorize this, we use this method, or we might use this method to try to decide what the result is and whether it's positive or negative, right? Well, we memorize that this one is going to be 0, right? So that whole thing goes away. I crossed with J, right? So I draw this up here, and I go I, J, K. I draw, remember, that's right there, is a positive K, right? Did I do that right? Yep. Yes. Okay. And you'll see it. This is in the book right here. Right here. You'll see that that's this guy right there. Right. That's that term. say we got I crossed with K, right? So if you go this way right here with the right-hand rule, you end up getting a negative J, right? So that's X and Z, and take a look at that right here. See, right there, negative J, right there, negative J. I don't know if it's J or Z. Okay. And then take, right here, we go cross. That's not a cross. This is the cross. This is the subscript X for the Q. And so J crossed with I right here. So we take this right here, and I believe we're going to get a negative K. Right? So that's Y, PY, and QX. There you go. Right here. See, it's negative K. And then this one right here is going to be 0, right? Because J crossed with J. And you get the idea. So you could do it this way, and you would be totally correct. But this is one way that's kind of like useful to us to set this up. As I mentioned before, in the bottom line up front, we can rearrange all of these things. So we take the determinant. And I believe Jack Breton has a video on taking the determinant of a 3x3. But let's just walk through it quickly here. If we're going to find, let's start out with the I. What we want to do is we're going to take this I and multiply it by the determinant here. So PY, PZ, QY, QZ, I. And then we need to memorize the fact that we want to go minus for the second one. So we take J, and then we take these two guys, right, in that one. So we go the determinant of PX, PZ, QX, and QZ. Whoops. And that's going to be times J. And then last one is going to be for K. We just separate this guy out right here. So PX, PY, QX, QY, and then K. Now we take the determinant of these individual ones, and that's going to be PY, QZ minus PZ, QY, I. I'm going to go minus. I'm going to go ahead and put minus in here, keep it going, and then go PX, QZ minus PZ, QX times J, and then plus PX, QY, you doing that way, and then minus PY, QX, and then K, right? And then if we wanted to just to fix this up, make it look a little prettier so we can compare it to the one on the previous page, I'm just going to rearrange, make that plus, and then go PZ, QX minus PX, QZ, J, right? I just flipped these two around because the minus and the minus. Because that's what you're going to see. That's how it's written in the book. Right? So take a peek back over to here, and you can see that all of those are identical. All right? So you got the Y and Z and the Z and Y. Y and Z and Z and Y. You got Z and X and X and Z. Z and X and X and Z. X and Y and X. X and Y and X. Now you can memorize this kind of thing, but I believe this approach right here will always do you right. Now we go on to section 3.1E. And I kind of thought maybe I should have done like an example, but we're going to know, because now remember that these previous sections right up here were really just vector review. All right, so we could have actually skipped this if you could remember this, but who remembers anything from one semester to another? I know I never did. So now we go back and use this is the application of them, and as I mentioned in the bottom line up front, if we want the moment about a point, now this is going to be the equivalent moment about a point, we take r, the position vector of the thing, and we cross it against the f. And if we wanted to find the magnitude of that, we will often, we could say the r, f, and if we happen to know the angle in there. But most of the time what we do in a practical situation where it's two-dimension, we just go ahead and try to figure out what that distance d is that's perpendicular. So we show that down here below. And we show that this, in the sign of it, all right, so we establish a sign, a positive and negative, where counterclockwise is positive and clockwise is negative. And that too obeys the right-hand rule, right? So just as a practical matter, this is the one that we're going to think about when we go and apply these things. Now, in my examples, which I'll put in a separate video, oh no, okay, I'm sorry, I have one more thing. In my samples where I put in a video, we almost always stick with 2D, right? It's only when we want to make sure that we can emphasize that we could do a 3D problem. Most of the time, I don't know if that's fair. We do a lot of 2D problems. That's in dynamics. We just stick with 2D because it's hard enough in 2D. 3 dimensions often will cause some additional concerns, but for the most part, we stick in 2D in dynamics. So we want to, but if we want to, so just recognize that this is the situation that we will look at quite often, and I definitely want you to be able to master this. I want you to be able to do this too. When we get to doing things with 3 dimensions, it's really better to go through meticulously and go through the mathematical process of take, and I think that the cross product is the most sensible way. Now, one thing that I'm going to introduce here is the idea, maybe I've alluded to it already, the idea of with respect to, right? Now, that means, so with respect to is sometimes I'll call, right? So, or with respect to, if I write R, A, B, right, means the distance, or not, maybe not the distance, but the position vector of A with respect to, misspelled that, with respect to B. That means that you're starting at B and you're looking at A, right? And one way to write this out is A with respect to B is equal to A XA minus XB, right? So this guy, that subscript kind of says this math right here, A minus B. So you can always think of it in those terms. And so when you're writing out a position vector, you look at the X, Y, and Z things. Like in the previous chapter, we wrote like dx and dy and dz. Here, let's make it just a little bit more formal. And then once you get to doing this right here, and I think it's actually the 4th example where we actually implement this and demonstrate it. So the first 3 sample problems I'm going to work through are really going to try to emphasize this concept right here. Right, this guy right here is probably the fundamental thing that we want to try to get, and I'm going to put it into the context of a free body diagram, some of the forces and some of the moments equaling 0 context, because I think that's the real important fundamental thing. The book decides to just use the idea of the equivalent moments. That's fine, but I want to emphasize the free body diagram context. We could also find the equivalent moments in a more complicated context by applying this right here. So that's going to be the fourth sample problem. The first three are going to be simply the application of a two-dimensional problem. So that's the lecture. Hopefully it'll take shorter in class.